So, question 3 is obviously a little more involved. So 3 of lead, 2 of phosphoric acid. It's going to produce 3 of hydrogen and 1 of lead 2 phosphate. So 3 moles, 2 moles, 3 moles, 1 mole. Now, in this case, the request was that you fill in both of these rows. So you have all that information. So 621.60 grams of lead, 196.00 grams. And again, we round off to 2 decimal places because we're basing it all on a triple beam balance, which we have access to when we're doing these masses. Okay? So that's a fair and proper rounding. Anytime we're having masses, just round them off to 2 decimal places. And then this one's a big one, 811.54 grams. Pretty heavy. Well, lead's a heavy metal, which makes sense. Now, before we plug in these other values, we have to find our limiting reactant first. There's a couple ways you can do this. I've taught the mole to mole, but some of you did the mass to mass, and that works too. Okay? If you do the mass to mass magic square, you'll still find the same limiting reactant. It'll produce less grams of the same product. Okay? So if we picked hydrogen, for example, and I'm not going to do all of them, just because that'll take time, too much time. So let's target for hydrogen and test for lead. So the lead is down here where it's being tested based on what you've been given. Okay. By comparison, across the way, we're going to test for hydrogen as well by using phosphoric acid. So, whichever of these produces less moles is the limiting reactant. We're going to run out of it. All right, so let's take a look. So, N of hydrogen, H2, over. Well, how many moles of lead do we have? And how do we figure that out? Don't worry, I want to identify who you are. Okay, never mind. We're shy. So what you're going to do is you're going to take your lead. I guess we have to sort of put this on pause, don't we? And go the number of moles of lead equals the mass of lead divided by the molar mass of lead. Whoops. Now, some of you made the mistake of using the mass from the chart above. That's a mistake, right? So we have 100 grams of lead over here, and the molar mass is 207.2 grams per mole. And based on this calculation, that leaves us 4 significant digits. So 0.4826. So that's the value that's going to go into that calculation. Okay. Put a pin in that one because we are going to need it later. Okay. Similarly, we have to figure that one out. Magic triangle. Okay, again, 100 grams. Over. 196. Grams per mole. Nope, sorry, my mistake. Divide that by 2. So we are 1.200. 1.020 moles. And that one. Then we carry on with the calculation. Back to the magic square. Three moles of that in the ideal, and 3 moles here as well. Right there and right there. So, that tells us that with 100 grams of lead, we're going to get this many moles for 826 moles of hydrogen out the other end. Okay, hydrogen is 3 moles. Phosphoric acid is 2 moles. So we just compare these two. Whichever one's less, that'll tell us what reactant. It's going to run out. So 4826 back up here. That means that there's going to be excess phosphoric acid left over as a result. Okay, so that's question A. How many grams of lead-2-phosphate are produced? So we're going here for our next target. Well, in this case, I would just use the mass to mass. That's the quickest way to go. Question B. Sorry. Again, we put our target up in the corner. That's our lead-2-phosphate. We have to use lead here because it's going to run out. If you used phosphoric acid or one of the other products, that'd be incorrect. Okay, so that's your 100 grams. That's all going to get used up. Okay, this bad boy here is 811 grams, 0.54 grams, over top of 621.60. Which brings us to a mass of 130.56. Again, round off to 2 decimal places for all your masses, because we can base that on our triple beam balance in the class. So, go back up here. There's a check for that. Determine how many molecules of hydrogen are produced. Okay, so that's N of H2. Well, this one's actually going to be pretty quick because I said to put a pin in it over here. We can use this piece of information right here to solve question C. So we can save ourselves that time. All right. So the number of molecules of hydrogen is equal to the number of moles of hydrogen times Avogadro's number, 0.4826. Again, molecules per mole. Equals 2.906 times 10 to the 23 molecules. For question D, we're trying to figure out, how much excess reactant is left over. Oh, I should not be remiss. I got to put these values in here. All right, 130.56 grams. And we use this value here. Oops. So that should be filled in there. The next thing we're going to find out is here, how much got used, and we're going to subtract that from 100 to find out how much is left over. So for that, we're going to use our magic square, our mass of H3PO4 used. Of course, we're going to base that on our limiting reactant. Oops. Again, 100 grams. So that all gets used up. Uh, 196 over 621. $31.53. Now, if there's a bit of a rounding error there for some of you, or you forgot to put the 3, that's fine. That wasn't a huge deal. I didn't take any marks off for that. That's okay. H3PO4 left equals 100. We want to get really tight about it. Go up. Total minus which leaves us with 68.47 left. Okay. And we want to go back to our top here and go 31.53 grams. Whoops, sorry. That doesn't go there. That goes here. Okay, so we found that as we were going. So used or found. So we have to fill that chart in as we go. We didn't find all of them or use all of them. We just have to be selective. Okay? And that's that.